All right, so technically we should be live now,
All
and
right.
I'm gonna go ahead and hang up the phone with you, and I'm gonna wait on Alex confirmation that he can hear both of us.
Okay.
All right, so I don't know if you're tuning in right now. We've had we've had a couple of issues to try to be on the air, and I think it's working now. I'm just waiting for a confirmation from Alex that he can hear both myself and Jake, so that we can go ahead and get started with the lecture. Jake, if you don't mind saying something right now, um, just so that we can
Sure.
confirm. Perhaps you introduce yourself.
Yeah, I'm Jake. Hello.
This is this is the best way that I know you, straight to the point, and that's it. So I'm just waiting for Alex's confirmation that he can hear you, Jake, and we can get started right here. So if you're tuning in, today we are going to do we're going through a case study that took place at NASA Langley for Predict. And okay, so I see so many people and saying sounds good and it's working. All right, awesome. So let's go ahead and get started. Um, so today's lecture is about a case study. And in this lecture, actually, it's more than just a case study. It's a guideline for every automated fiber placement project out there. There's a chart that I got a lot of questions recently, like, do you think we should do this? We should do dry runs, we should do that. And throughout this lecture, we're going to be talking about this. But before I go ahead and get started, um, approximately 2 weeks ago, I don't remember even what was the discussion. And I said, if I had to pick my colleague from everyone all over the world, it would be someone named Jake Turry. And Jake I call you a process planner, but I mean, you can identify yourself. I mean, you're a process planner for me. You're someone that match makes design and manufacturing. Um, Jake, why don't you introduce yourself a little bit?
Sure. Well, my I guess my official title at NASA is engineer,
All right. Can
and
you?
I've been there about 8 years now.
Awesome. So, Jake, for people who are joining in, okay, you're such a minimalist. You don't want to even talk about yourself. I'm gonna brag about you. Um, Jake, Jake knows how to program AFP machines. Jake knows how to run AFP machines. So very often, it's very hard to have someone who can like. So if this course is composites A to Z, if it was AFP A to Z, Jake would be the person to go. I'm gonna go ahead and introduce you, and he's just awesome to work with. All right, so Jake, we're gonna be talking about the manufacturing of the wind tunnel blades. This is coming from the SAMPI paper that we had last year, and of course, so many other people worked in this. To recognize them: Don Jigley, the Isaac Lead, Ray Grenoble, Joshua Halbritter, Brian Mason, Chris Kassan, Susan Waltz. So many people helped. Nancy Holloway. So many people helped in the scenes and behind the scenes. Today's lecture is going to be a little bit, we're going to introduce Isaac, and I'm going to let you talk about Isaac. I call Isaac my best friend, and I guess if you had a name for it, it would be your baby. And then we're going to talk about wind turbine blades and what's like specific about them, what's complicated. And this is the section process planning. I believe this is a standard that we came up with, And I urge everyone who wants to do any AFP project to take the Langley's flowchart that we're going to introduce today and use it as it is. This is the best. I mean, we've had hours and hours and hours of discussion all together to come up with this with the whole Isaac team. We'll move on to manufacturing and some concluding remarks. Does this sound good for you, Jake?
It does.
All right, awesome. So tell us a little bit, what are we seeing in here? This is the Isaac robot. What's special about Isaac?
Well, Isaac is a as you said to me, it's my baby. It's a KUKA Titan 1000 robot that's been modified by Electro Impact to be an AFP platform. So essentially, our main use for it is as AFP, and that currently there's an AFP head attached to the robot itself, but it's a platform. We also have stitching head. We have ultrasonic knife head for cutting. We have a laser projection head for projecting CAD geometry onto a surface. And we have a blank element head for attaching any other tools we may need.
All right, awesome. So and in this picture, it shows one side of Isaac, which is the table, the placement on the flat table. We also have a rotator on the left side where we can have an added degree of motion, an eighth degree freedom. All right, so this is the workflow.
And the robot itself has 6.
Say again?
Oh, I was just going to clarify. The robot itself has 6 degrees of motion. 7th degree is provided by the rail, and the 8th degree is the
All right, awesome. So this is the workflow that I was talking about. This is something that at Langley, if someone comes to, hey, we want to manufacture something with an AFP machine, how do we go ahead and go about it? So basically what we see in here is different sections. One of the sections that we have is the design assessment. So yesterday we talked about this a lot, and Jake, isn't it after you finish the CAD model, you click File, Print, and it creates for you an AFP part? Isn't it that simple?
In a perfect world, yes, but in reality, it's not nearly that.
Actually, it is very impressive how many folks don't realize that manufacturing messes up their design. And this is why to manufacture something with AFP, folks needs to bring their design and do design assessment with the manufacturing team. And I'd like to call this manufacturing informed design. So this is where we do a lot of design assessments. We propose refinement. We do this DFM study. We validate that geometry. And then from there, we go 2 ways. One of them is, let's say, programming related. And the term programming is not sufficient, but it is programming related. This is where we do select property selection, NC code generation, virtual simulation, playbook creation, and then we do air runs. So this is in the first part. What do we learn from an air run, Jake? Why an air run is important?
Well, one of the main things is whether or not, as a programmer, I do my job properly. So when I first program something, I simulate it on a robot to make sure it's going to be able to. But a virtual robot is still a virtual robot. So the air run lets me put my program on the actual robot to ensure that it's going to behave the way I want, and it is going to be able to actually reach all the points on a tool that it needs to go.
So, Jake, one thing I'm going to ask you, for some reason, I don't know if it's only me or if it's for everyone, some reason when you're talking, the bandwidth is cutting off some words. So if you can just, whenever you want to talk, just like do it a little bit slowly. Like this, having these gaps will help the buffer to actually catch up with your words. Do you mind repeating what you said about the error runs?
Sure. So when I first programmed something, I run it on a virtual robot to ensure that I can reach every point in the tool that I want.
All right.
However, that's still a virtual robot, so there's no guarantee that the virtual robot will perfectly match the real robot.
All right. So I'm gonna do something because I get you very, very well.
So we
So what sometimes when you say something and I like see the bandwidth has cut off, I'm gonna go ahead and repeat it myself like this. People will get your answer in case like I see some of the cut off the bandwidths. Apparently it's Saturday and the internet is now full speed with streaming and everyone trying to relax a little bit from the week. So what you refer to is in process planning, we have these two steps. The first step is when you do the programming and you do the verification on the virtual robot. But a virtual robot is a virtual robot, as you said. And this is why we take the code and we run it on the actual robot without having the part in place, without having anything in place. And like this, we can verify that the motion that was programmed is accessible by the hardware. And there is no differences between the software limits and the hardware limit that actually is preventing us from getting a functional code. So that's from one side. The other side is the tool for manufacturing. And tool for manufacturing, this is where we do 3D printed prototypes. We take them to the cell, and we're going to talk in detail about it today. And basically, a tool is so expensive, Jake, right?
It is.
And so it is much more logical and much better to try to 3D print something that can withstand a couple of times before you go ahead and invest $500,000 and into a tool. And this is what we did in this case study. And then we move on to a dry run. So a dry run, what is a dry run?
Well, with the dry run, it's similar to an error run. We run the robot with no tool.
All right. So basically, the air run, there is no tool. The dry run, there is a tool, and we are running the AFP machine, but without the material.
Yes.
All right. So here you have it, folks. If you want to do an AFP project, this is a workflow of Isaac at NASA Langley. This is something that you can adapt for your own equipment, own hardware. This is, of course, for new projects. We're not talking here about something that you've been manufacturing on the same machine for years and years. If you want to undertake a new AFP project, that's the best method to go with. Design assessment, talk with the designers. Once you finish this design, move into two stages. One will get you a functional code, one will get you a functional tool. From the functional code and the functional tool, you can do a dry run. This is with the tool in place, but without extracting material. And then finally, you go through the AFP process. Jake, what does the plybook, what is this method of plybook helps us achieve?
Well, the plybook for us has been pretty invaluable. Basically, since we don't do production, we may build one thing, and then 6 months later, a researcher wants to build another one. And it's tempting to believe that you can remember what you did 6 months ago. That's not the case. So with the plybook, we're able to capture all of our process parameters. We're able to capture operating temperature, how much pressure we're putting on a tool, how fast we're running, how much we're using, and we can record any flaws or any concerns we had. That way, the next time we go back to the part, we can improve upon it based on our record in the plybook.
Awesome. And this is where we, I don't know if the mouse appears when I move it, but this is where we record basically when we start manufacturing, when we end manufacturing, all these process parameters, the machine conditions, the feed rate, and if there are flows, if we need to correct pictures and so on, and we have access to the geometry itself. All right, so this case study is about the manufacturing of wind tunnel blades. And these tunnel blades were done long ago. There's not much of archive for even the geometry that they were manufactured with. And they are needed to like create new sets to replace old ones in wind tunnel blades. And therefore, this project, the Predict project, um, what does Predict stands for, Jake?
Well, NASA loves its acronym, and Predict is one of those acronyms. It's preparing researchers to evaluate and develop impact-driven collaborative technologies.
All right, I worked on Predict for so long. I'll never memorize it, but I know that the acronym is Predict. So, all right, awesome. Thank you for at least being capable of saying that. So this is the project. We used a Faro arm to actually recapture because there was unfortunately no computer model was available for this blade. So we did some reverse engineering, some data acquisition, some model reconstruction. Basically, all of this is to reobtain the CAD model as we didn't have access to the CAD model. And this model reconstruction, basically what we did is like the outer surface, we created it through these profile sweeping, and we got cloud of points, and then these cloud of points, we got the curves, the profiles. It does look like a wing as well. Don't you agree?
It does.
So then we created the outer mold line. So the outer mold line is oftentimes when we have a shape, and this is what you want to obtain, you have to do the inverse of that shape. And this is the outer mold line, and the tool has to withstand compaction by AFP. What is compaction, Jake?
Well, when we're laying up with an AFP machine, material that we want to adhere to the surface, and the best way to do that is with a IR heater, and then a compaction roller. A roller provides force on the surface and causes those to adhere.
That's awesome. So basically, the tool that we're going to use in the AFP manufacturing will withstand some heat and a lot of pressure during the layup. But then again, that's not the full story. Then again, it has to go through a cure cycle. And within that cure cycle, it has to withstand the pressure temperature cure cycle. So definitely making a tool out of a material such as Invar or so on is the best way to go, but not if you're starting a new project and you are exploring. If you're starting a new project and you are exploring, the best thing is to do is to create a tool form with 3D printing, and we're going to talk a little bit about that. So following that, we created the outer mold line. We thought of the best complicated place that we can actually create a subsection region that has inflection, that has complexity. So unlike some of these parts of the outer mold line, and then what we did is we created the ply boundaries and we left some runout area. So I say you're a process planner. I believe I'm a process planner. And by the way, I wore my Isaac shirt as well today. I see both of us, we have our Isaac shirts on. Process planning, which is both what we do, is when we are attempting to create matchmaking between the design and the manufacturing process while taking into account material, geometry. Basically, it's assessing if something can be AFP'd or not before being far too along and actually losing a lot of money. And this includes so many things like the toolpath generation, the validation of joint limits, and the understanding of heater collisions. I know that this is very frustrating. When you create a code, you think, hey, it's the most beautiful that happens, and then you go to the machine and you discover that a joint is not, you can't do that. And we do have a lot of those, right?
Exactly. Usually the simulation is pretty good about warning us. On occasion, we have had things simulate, then went to the actual program and got an error.
Awesome. All right, so these are some examples that I'm gonna go through them. This is an example of, so basically we use at Langley, you use actually VCP by CG Tech, and we had a presentation by Andre a couple of days ago on this, Andre Colvin from CG Tech, just to explain to people what we're seeing in here. This is what's a simulation in green, this cylindrical thing, that is a roller, and these are the different roller positions. So basically, as we're doing the layup, the red element in here is the heater. This is the heater model. And this is where we see if there is a collision between the heater and the tool that we are manufacturing on. This is the tool surface. And what you see in yellow and in blue, these are the courses. As you remember, we create our composite part by laying up course next to each course. So these are different simulation of different courses. So we have in here two things. So I'm going to talk about the first one on the left. This is a joint axis. Basically, a joint limit on the actual hardware was not respected through the programming, and this is calling on you to change a little bit the robotic orientation in order to do the manufacturing. What is going on the right picture, this collision area? What is that, Jake?
Well, that is VCS, our simulation program, warning us that if we actually run this program on a tool, we'll run a heater into the tool.
So basically, what we see in here is a problem. The simulation software is saying that we're going to have a collision in here, and you better align your orientation in a way, or it's going to be costing us a lot of money.
Exactly.
Awesome. So this is a little bit what we've done, and this is to confirm this workflow. What we've done, and this is good. So oftentimes when we have to do such a project, we even before we 3D print something that is as big as the final part, and whenever I say 3D printing, I think of Brian Mason. We 3D print a small small part, and you take it inside the cell, and you just sit around it and talk, try to do some joints with the robot, try to have a first assessment, a first feeling. But what we did in here is we validated the concept with a prototype tool that costed us like a couple $100, but it is the actual size of the tool, and we placed it there to make sure that without, of course, applying compaction, because compaction in here would actually be detrimental. Then we moved on to manufacturing the actual tool. So a lot of study has been done. Actually, there is a paper by, I guess, Brian Mason, Daniel Munden, and the crew on the finite element analysis required to determine the internal structure. And then we 3D printed a tool with Ultim that the cost was approximately $18,000. This tool, Jake, we were capable of doing the AFP layup on with compaction, but also curing several cycles. Is that correct?
Exactly. Plus, being able to 3D print it meant it was cheaper, and we could get it significantly faster than if we did it out of aluminum, Invar, or carbon.
Yeah, actually, you highlighted a very important point. It's much cheaper that is given, but it's also we got it much faster because it was 3D printed in-house. Some tests that were done in-house, and a couple of weeks we were running and capable of manufacturing. And this is the heart of the story. So once we finished from the programming, we finished from the workflow, we finished from all of these different elements. What we did is the actual placement, and we can see in here the manufacturing. Uh, so what we see in black is the composite material. This is the tool, and we have the run out places, and this is the robotic head. So this is the AFP head. On the AFP head, you can see very, very clearly the IR heaters. And by the way, Jake, there's so many people that are clapping and saying hello on the, so Dahval, Margaret, Elio, Nancy Holloway is on, Connie Jackson, composite specialists are on, Andrea Stolzen, Ali El-Zahrani. So many folks are saying hello and mentioning so many things. So I just transmitting that to you. And so, and after that, we go around and we take a look after each layup. We make sure that the splices are, if it's an AFP defect, but sometimes we accept it, sometimes we don't, and we have to replace and do the arts and craft. Do you agree with this name, arts and crafts?
That's a good description. You'd think that because we have this massive robot that's it, build it, and we move on. But there's lots of handwork to do inspections, replace splices and other defects. So arts and crafts is a good term.
Yeah, there's a lot of time we have to do a lot of manual fixing. And this is to wrap up the story. This is the final part, and we can see the complexity of the part and the inflection that we have. So it was manufactured. This is what we call a MDU, manufacturing demonstration unit. It was manufactured with Toray material, 190 GSM, and of course a quarter inch. This is the AFP machine that we have. And this was a good start for the project. That was almost more than a year ago. Since then, we made much more progress, and looking forward to be presenting that in future rounds. So basically, this is a composite manufacturing demonstration unit in the shape of a wind tunnel plane. This is to assess AFP applicability to such complex shapes. But what's one of the most important things that we've done is, and I'm gonna go back to the slide, is throughout all of this, we have defined the optimal workflow for anyone conducting a AFP workflow. I'm gonna change the layout a little bit. Perhaps I would consume a little bit less of the bandwidth, and we can actually talk a little bit together and see if someone has any questions. So I am changing the layout a little bit. Here we go. Hopefully that works. And all right, so this is it. This was the lecture we had for today. If anyone has any questions for any of like for Jake or for me, go ahead and let us know. This is the right time for it, and we can go through them. Jake, would you like to say any closing comments at this time?
Well, this was a very fun project to work on, and I got to work with you, and one of my favorite people to work with.
All right, this is awesome. Thank you so much, Jake. I'm gonna give folks a couple of. I see tons of claps on LinkedIn, and people are very happy with this. If there is any more questions, just let us know. So I'm gonna go ahead and close it, Jake. Thank you so much. What I have is on the archive page. I also added your
Thank you.
LinkedIn so people can enter in touch with you in case they want to. All right.
All right, thank you, everyone.
All right. Bye bye. Thank you so much. And tomorrow will be the last summary. It's the week 4 summary as we're gearing up towards the final 4 or 5 lectures for our months. Thank you so much and talk to you tomorrow. Bye bye, Jake.
Bye.